This lesson is about confidence intervals. So before we start it, I want to review a few things that have to do with notation. My first thing is, if I have a p in this context, the p represents the proportion. It represents a proportion of success for the entire population. And just a reminder that we call P a parameter. So remember, when we are working with populations, our measurements are called parameters. And you might be able to guess that P hat is actually an example of a statistic. So this is going to be the proportion of our sample, or sample proportion. And as I said, it is a statistic, which is a measure of a sample. Also, Q is just going to be 1 minus P. Q hat is just going to be 1 minus P hat. So now that we have those done, I'll give you a short definition of a confidence interval, and then we'll actually do an example of one. So a confidence interval is an interval that estimates a parameter. So oftentimes it's really hard to find a population parameter because most populations are just too big. So you take a sample, and when you take the sample, you usually will find a proportion that we call the statistic. So this is a way for us to be not quite certain but confident of where our actual population parameter lies. So under our first example, we know that your local newspaper polls a random sample of 333 voters, finding 144 who say they will vote yes on the upcoming school budget. We're going to create a confidence interval. So in this example, the population is going to be all voters. The sample is actually just going to be the 333 that we found. Or the 330, excuse me. Our P is going to represent the proportion of people, of the entire population of voters that will vote for the budget. And the P hat is going to represent the proportion of our sample that will vote for the budget. So I'm not going to write out the Q and the Q hat, but the Q represents the proportion of all of the voters that will vote no on the budget. The Q hat represents the proportion of the sample who will vote no on the budget. So in this case, we actually don't know what our regular P is. We don't know what the proportion of all voters who are going to vote for the budget is. We're going to estimate that using a confidence interval. We do, however, know what our P hat is. So our P hat is the proportion of our sample that are going to vote for it. And we know that out of 330 voters, 144 are going to say yes, which tells us that our proportion is about 0.436. You're going to find your Q hat by doing 1 minus that, and you get 0.564. The last thing that we need is our N, which is our sample size, and it's going to be 330. You don't have to start by writing all these out, but I think it'll make the problem a lot easier if you at least write these 3 measurements out before you do any work. Rather than just trying to go through the problem quickly, you'll be more likely to get it right if you start by at least writing out what you know. So as with the previous section, we do have to start out by checking conditions. We will be using a normal model, and one of our the necessary things when we use a normal model is that we always need to check our conditions. So the first thing I'm going to check, I'm just going to check everything. As I said in the previous video, there are some that you can skip, but I'm just going to make a few assumptions. First of all, we are going to assume that all the responses are independent of each other. And this is a reasonable thing to assume. So just make sure you do make that assumption. Make sure it's reasonable. And the second thing we know is this is a random sample. We also know that we don't necessarily know this, but we're going to just make the assumption that 330 is less than 10% of the whole population. This seems like a reasonable thing to assume. And I'm going to actually say less than 10% of all voters. The last thing we need to do is our success failure. So for the success failure, we're going to use our NP hat and we're going to use our NQ hat. When you multiply those two out, which I recommend that you just do on your calculator, just in case, you will end up getting that both things are much greater than 10. So since all the conditions check out, we can use a normal model. And I'm actually even going to write all this out. Since conditions are satisfied, we can use a normal model. It's a good idea if you're taking the AP test just to mention the normal model somewhere in here, just so the readers know what you're doing. They probably won't mark off if you don't say that, but it doesn't hurt. So our formula for a confidence interval, I'll write it out and then I'll explain it. So our formula is going to be p hat plus or minus z star times the standard error. So it's a long formula. It doesn't look so long right now, but once you do it, you'll think it's really long. But I'll explain these things one by one. So the first thing that we know is we know our p hat. We actually had that in the previous slide, and that is just our proportion of success. You can call it your mean in this case if you want to, because when we use our normal model, we're actually going to make that our mean. And I'm going to kind of draw a normal model on the side. So for this normal model, right in the middle of it is the 0.436. The next thing that I want to know is this z star. So you might remember we did use z-scores before. And what I'm going to do, I'm going to call this my critical value. And I want to talk about what this is actually going to mean. So here I said 95% confidence. I didn't say that in the initial thing. Usually if they don't say what confidence level they use, most of the time it's going to be 95, but just double check and make sure that you know which one you're using. So what you're going to be looking at is you're going to look at around this mean of 0.436. You want to know what values are going to fall within 95% of this. Now, if you remember, the 95% goes from a z-score of -2 to a z-score of +2. So actually, our critical value in this case is going to be z star equals 2. And 2, believe it or not, I'll just tell you this right now so that you aren't completely freaked out in the next problem. But I'll just warn you now, 2 is actually an estimate that we often use with normal models. I'll tell you what the actual better value is in just a minute or two. So we know our z is 2 because we want to take our mean and we want to find all of the possible values that are 95% around the mean. So I know that my p hat is going to be 0.436. I have those 2. The last thing I need to find is called my standard error. So first thing I'm going to give you is the formula for it, and then I'll talk about it. So the standard error, we actually sometimes write as a standard error of p hat. The formula for that is just going to be p hat times q hat over n. Now, if this looks familiar, there's a good reason for that. In actuality, the standard error is a type of standard deviation. However, in this case, we're taking the standard deviation of only the sample. So we're not using the entire population because we don't actually know our population proportion. We're just going to use the sample. So really, all this is the same thing as the standard deviation, just has a different name and a slightly different context. So when you calculate this out, you will end up getting about 0.027. And once you have that, you can actually do the rest of the problem. So before we actually finish this up, there's one more thing I want to bring up. It's called our margin of error. And sometimes we abbreviate it, by the way, as ME. So in this case, my margin in this type of confidence interval, and I think actually for the rest of the ones in this chapter, my margin of error is just going to be my critical value, my z star, multiplied by my standard error. So in this case, it's just going to be 2 multiplied by 0.27. So back to the formula that I had. I had p hat plus or minus z star times the standard error. So I'm going to use my p hat, which is 0.436, plus or minus z star times the standard error. Oops, I never calculated this out. It's 0.054. And so remember, this is the margin of error. So then there are 2 ways that you can write this answer. You can either stop here. However, the way that I prefer you to write it is to actually calculate this out. And so you're going to start by doing, go least to greatest, by the way. First thing you do is the 0.436 minus 0.054, which gives you 0.382. Then you do the same thing, but with plus. Which gives you 0.49. So then this is my preferred answer for my confidence interval. So what this is telling me is that we don't know the exact population of voters, but we're pretty sure that it's going to be between 38.2 and 49%. So in order to write our conclusion for this, we're going to say that we are 95% confident, or you can say I am 95% confident that the actual number of voters that will vote yes is going to be between 38.2% and 49%. So I will just say that between 38.2% and 49% of voters will vote yes. So for our second example, I'm going to do one extra thing on this one. You can try it on your own, but there is one thing I want to point out before you do it. So before you try the problem, I do want to tell you that in the last one, I was telling you that 95% confidence means that you're going to look at the middle 95%. Previously, I said that the z-scores were between -2 and 2. Now, this is a good estimate of those, but in actuality, the actual value, if you want to be more precise, would be 1.96. So what we're going to do is we are going to use our critical value of 1.96. So now if you want to, you can feel free to try the rest of the problem. Otherwise, you can just watch me do it. So you're always going to want to start out with your conditions. I would like you to do those on your own, please. Conditions on your own. And from there, you're going to use, you can find that your p hat is going to be 0.27. We know that our n is 53. So once you have your p hat, we know that that's going to go in the middle of our confidence interval. And the only thing we really need to do is calculate out our standard error, which remember has a formula of p hat times q hat over n. I forgot to write my q hat out, but I'm going to just add it in. It is going to be 0.73. So when I calculate this out, I will end up doing 0.27 times 0.73 all over 53. And after I take the square root of that, I get approximately 0.061. So then, from there, I am just going to use my formula from the previous section. I'm going to do the p hat plus or minus my margin of error, which is going to be, actually in this case, it's now 1.96 times my standard error. And that gives me 0.27 plus or minus 0.1195. I'm actually going to round that to 0.27 plus or minus 0.12, just because I'm a little lazy. So when you do that, you end up getting 0.15 up to 0.39. So you'll find that this is actually a super, super large confidence interval. So we're confident that the improvement rate is going to be between 15% and 39%. That is a huge, huge, huge amount. So in order to try to get a better estimate, we're actually going to make it a little bit less confident. So we're going to use a smaller confidence interval. And so, for example, number 3, we are going to do the same thing, but now I want to change it to 95% confidence, or 90% confidence. And in class, I will show you how you can actually find the critical value for these. I'll just tell you right now that your critical value for 90% confidence is 1.645. And then from there, we're going to use the same exact values. So our p hat is still going to be 0.27. Our q hat is still 0.73. Our n is still 53. Because these three are all the same, our standard error actually is not going to change, thankfully. So we don't have to calculate that out again. And so the only thing that's going to change in my confidence interval is my critical value. So I'm now going to write it as 0.27 plus or minus 0.061 times 1.645. That gives me 0.27 plus or minus about 0.1003. I'm just going to write plus or minus 0.1. So I end up getting 0.17 to 0.37. It's still not as precise as I would like, but it's a little bit better. So you'll find that in order to have a better interval that's smaller, you actually are going to have to be less confident about it. I'm going to talk about what confidence actually means in class tomorrow, but for now, just know that the more confident you are, the larger your interval is going to be. Now, you'll find out that there's another way around that in order to be slightly more confident and have a smaller interval, and that is actually to decrease your margin of error, which you can do by changing your sample size. So when you have a bigger sample size, it'll be slightly better. So what we're going to do in the next problem is we are going to find out how to estimate the sample size that you would actually need to have a certain confidence level. So for this one, I'm going to be super duper ambitious. I would like to find a 98% confidence interval with a margin of error of plus or minus 5%. So it's a small interval, it's a high confidence. So now I'm going to figure out, what do I need my sample size to be? Now, if you remember, our margin of error formula is z star times my standard error. So in this case, I know the margin of error I want. I know the confidence level I want. I don't know a few things. However, I do know that my p hat is still 0.27. I do know that my q hat is still 0.73. My n is actually what I'm trying to find. They asked me what sample size. So the ME, my margin of error, must be plus or minus 5%, so I'm going to write it as 0.05. The last thing I need is my Z star. Now, as I said before, I will show you in class how to calculate it. If you're actually in the CP class, I'm just going to give you all the Z stars before your quiz, so you'll have them to look at. So I'll tell you right now that the Z star for 98% confidence is 2.326. So now what we're going to do is we are going to use algebra in order to solve this problem out. So rewriting this formula, we know that our standard error is the square root of p hat q hat over n. So we know a few things here. We know our margin of error is 0.05. We know our z star is 2.326. We also know our q hat and our p hat. So they're 0.27 and 0.73. Now, many of you, if you're really good at algebra, you can go ahead and just work this out on your own. If algebra is not your strongest subject, then you can watch as I work it out. So first thing we're going to do is divide both sides by 2.326. Your left-hand side is now going to become 0.0215. Your right-hand side actually is just going to be this radical. The next thing I'm going to do is get rid of the square root by squaring both sides. So on my left-hand side, I'm now going to have 0.00046. Right-hand side, I'm actually going to simplify the stuff in the parentheses. When I do that, I will get 0.1971, and this is over n. My recommendation is that if you can keep any of this stuff in your calculator, do it. If you know how to store numbers, it'll help a lot. Then you won't have weird rounding mistakes. If you're not sure about how to store numbers, then I can help you in class. I'm actually doing this on a cell phone calculator right now, so my answers are going to be a little bit weird. You might even get something more precise than me. If you do, just let me know in class, and I'm happy to give you a reward sticker for that. So then, my next step on this one is to move over this n. It's in the denominator. Having variables in the denominator is just horrible, so what we're going to do is we're going to multiply both sides by n. The right-hand side, my n's are going to cancel out. So I am now left with 0.00046n equals 0.1971. The last thing I'm going to do is divide both sides by this long decimal. When I do that, I get n equals 428.478. Now, if you got something a little bit different, because you did better calculator input than I did, then that's great. You'll find that you and the people around you are probably going to get different answers because of rounding, but the more stuff that you keep in the calculator, the better your answer will be. So now, we are not going to use a sample size of 428.478. I'm not sure how we could find a 0.478 of a person, but it's not going to happen. So what we're going to do is we are going to round up. You're always going to go up, even if you have a small number that you would usually round down, we're just going to go up. So I'm going to say we should sample 429 people. So that's how we can find a smaller margin of error, but higher confidence is by sampling more people.